Hello everyone, and welcome to my presentation. My name is Christoph Weibel, and I'm a postdoc at ETH Zurich. In today's presentation, I'm going to talk about fitness landscape analysis metrics that are based on Sobol indices and fitness and state distributions. This work has been co-authored by Georges Martides and Yongwei Zhang. The motivation for this work comes from trying to solve real-world engineering problems. My background is actually in building engineering, where we use simulation-based optimization for the design of energy-efficient buildings and neighborhoods. And especially in this domain, many problems are not very repetitive. And we also know very little about problem structures of the problems that we're trying to solve. But all this knowledge would be very useful if we want to make good decisions on selecting an appropriate optimization algorithm and also on tuning its hyperparameters. So this is why we're interested in fitness landscape analysis in general. Now, looking at the existing literature in FLA, it seems rather unclear which metrics are the objectively best ones to use, especially if we have no idea at all of the problems that we're trying to solve. Furthermore, the literature states that generally using several metrics is required if you really want to get an idea of the overall problem structure. So since problems can be very diverse in their characteristics, you also need a number of different metrics to capture this diversity. And therefore, in this paper, we are proposing 6 new fitness landscape analysis metrics. 2 of them, they are based on the Sobol method, Vinter and VCV. And the Sobol method is a common technique in global sensitivity analysis. Specifically, these 2 metrics inform on the degree of variable interaction. And the second metric quantifies the difference of individual variable sensitivity. Then we have 4 metrics that are based on fitness and state distributions, and specifically we compute their variance and the skewness. All of these 6 metrics can be used for static fitness landscape analysis, and actually this talk and this paper is only focusing on static FLA. However, in principle, the latter fork could also be used in dynamic or exploratory FLA. Now in the following slides, I will go through each of these new metrics individually, and I will explain what they mean and how they can be interpreted using these 4 test functions from the COCO set. The first metric that we will be looking at is the degree of variable interaction, Vinter. And this one is computed based on the first order effect Sobol index, SI. And this one measures the how much one individual decision variable in a problem contributes to the output variance, so to the cost function value. And if we look at the sphere function as an example, the landscape is shown as a 2-dimensional problem, but we're actually computing metrics for 10-dimensional problems. So in this stacked bar plot, each of the segments, they correspond to one of the 10 decision variables of the problem. And what we can see here is that 3 of these segments are larger than the rest. And that means that these 3 parameters particularly, they contribute more to the output variance or to the cost function value than the remaining parameters. They also sum up to 1 in this case. And now what the degree of variable interaction Vinter does is it's computing 1 minus the sum of these segments. And in this case, that results in 0. And what this means is that for this particular problem, the sphere function, there's no variable interaction, meaning that the parameters themselves, they don't interact with each other. And such information can be really useful, because then you can apply sequential optimization techniques or decomposition techniques that might be very useful for let's say, expensive optimization or high-dimensional problems. Looking at the ellipsoidal function, again, we have a very low value for Vinter. And what is interesting to note here is that there seems to be one parameter that is very important for the cost function value. whereas the other ones seem to be less important. However, in total, they sum up to 1 or close to 1. That means, again, variable interaction does not seem to be important for this problem. In this problem, in the Weierstrass function, however, the individual segments are very small, and that means that individually these parameters do not contribute much to the output variance. And therefore, the value for this metric for Vinter takes a very high value. So this problem indicates, or the metric here indicates that this problem is not separable. For this problem, Gallagher's 21 peaks function, again, the individual parameters individually seem to not contribute too much to the total output variance, therefore indicating that this problem might be non-separable, also shown by a relatively large value for Vinter. The second metric that is based on the Sobol method is the coefficient of variation in variable sensitivity, WCCI. And it is similar to the previous one, but in this case, we require the computation of the total order effect Sobol index, ST. And what this one shows is it computes the significance of an individual variable, xi, considering also the interaction effects with other parameters. And again, looking at the sphere function, we can see that 3 of these segments, 3 of these variables, are more important. Now, what WCCI, this new metric, indicates, shown as star marker, is how different the individual contributions are in this problem, or how different the individual segments are. And in this case, we have 3 more important variables, or 3 larger segments, and then remaining smaller segments. So there's a bit of a variation here. Therefore, this value takes the metric takes this value in this case. Looking at the ellipsoidal function, the metric becomes quite clear. So for this problem, it takes a really high value for WCCI, and this can be explained by having one parameter only that is contributing almost entirely to the cost function value. The Weierstrass function and Gallagher's function, these are cases where the variation in variable sensitivity is relatively low, because as can be seen here, the individual segments are relatively similar or homogeneous. And that means that in these 2 cases, individual parameters seem to be equally important. Moving over to the fitness variance and fitness skewness, these are relatively straightforward to explain. Now, again, looking at the sphere function, if we sample it using, for example, Monte Carlo, we can plot the occurring cost function values in the histogram. And really all that we're doing here is computing the variance of this histogram and the skewness. For the skewness, however, we're not centering it around its mean as the regular third central statistical moment would do it, but we center it at the center of the minimum and the maximum occurring cost function values. And we do that to get a better understanding, or to obtain a more interpretable result for this skewness metric, which is also normalized between -1 and +1. Looking how these 2 metrics behave for our 4 examples, comparing the sphere and the ellipsoidal function, the sphere function seems to have a lower skewness than the ellipsoidal function, but also a lower variance than the ellipsoidal function. This can be seen in these distributions. And the Weierstrass function, again, a bit higher skewness here to the left, but also lower variance. And Gallagher's function has a very low variance, as can be seen here in this histogram, but also a very large negative skewness. And such information can be really useful for algorithm selection and parameter tuning, because if you know that most of your values are clustered at very high cost solutions, then yeah, you get an understanding of how your probabilistic methods might behave, and you might get an idea how you would need to trade off between exploration and exploitation in an optimization algorithm. For the two last metrics, the state skewness and the state variance, we first need to introduce this new distance measure, which we call the state dispersion. And you can imagine that by plotting a fitness distance correlation plot, so this one is an FDC plot for the sphere function, and overlaying the cost function value histogram that you have seen before to this FDC plot. Now what we're doing here is then for each bin of this histogram, and for illustrative purposes, we are combining several bins together, just that it's more easy to read. But this one you could understand as being one bin. So for each bin in this histogram, we are now computing the mean distance of this FDC plot that occurs in this bin. And looking at this segment, for example, there's a relatively large state dispersion. But if you now look at a domain, for example, here at very high cost function values, the state dispersion is much smaller. And again, such information can be really useful, because then if you know that let's say close to the global optimum in terms of function value, so close to here, many solutions are actually very different in terms of the state. Then yes, you will know that you might need to maintain certain perturbation mechanics in your optimization algorithm. Whereas if you know that all solutions that are coming close to your optimal solution are also similar state-wise, then you can, for example, switch towards a local optimization algorithm. So this distance measure we use for the state variance and the state skewness, mu2 of d and s of d. And we can plot this as solid black curve over the cost function value histograms from before, now highlighted in orange. The dashed lines indicate the maximal and the minimal state dispersion that occur at a certain histogram bin. But we're really only using the mean state dispersion. Yes, so if we now consider this state dispersion as a probability distribution, we can again compute its variance and its skewness. And that's what's shown here for the sphere function. In this case, there seems to be no skewness in this distribution, and yes, a certain variance. And if we compare this to the ellipsoidal function, we can see again the skewness there's almost no skewness, and also relatively, or this amount of variance. Looking at the Weierstrass function, I think this is where it becomes a bit more interesting. Here the skewness becomes larger, because as you can see here in how the state dispersion behaves, it drops towards high cost solutions. And this means that at these domains, or at very high cost solutions, most of the samples are very close state-wise. So if you end up in this domain with the optimization algorithm, yes, you know that most of the bad solutions are all clustered together in this state domain. Looking at Gallagher's function, we can observe a negative skewness of state dispersion, which can be read here. And again, this will tell you that at very high cost solutions, the variety of states is very high as well. So all of these solutions might have similar high cost function values, but they're all very different state-wise. And what you can also see here is this orange marker, this spike. We introduce a condition that if at a certain histogram bar, there are only very few samples, we basically discard this domain. And we do this to get a more consistent and less random metric value for this. Now, this concludes the introduction of the new metrics. What we did now was to compare our new metrics with existing established metrics from the literature. And we are computing the metrics for 1,500 problems and problem instances in 2, 5, and 10 dimensions. And for each of the metric pairs, so FTC versus autocorrelation, for example, FTC versus information content, and so on. For each of the pairs, we conduct statistical tests, these ones. And this will result in the matrix, here shown for 10-dimensional problems. And on the top right are the p-values of the statistical tests for each of the combinations. And on the bottom left are scatter plots when plotting one metric against another. And what we can see here in short is that for most tests, we can see a significant difference. And only in very few instances, we could not observe a significant difference in metrics. And what this might indicate now is that this can be interpreted as our new metrics showing new perspectives on fitness landscapes, since the distributions of these metrics are different than the metric distributions created by the other metrics. Zooming into some of these scatter plots, we can actually see that some of the metric pairs seem to correlate somehow. And for other pairs, for example, the FTC plotted against the variance in the state variance seems to be rather random. So also again here, just by plotting two metrics against each other, we could get an indication if metrics are complementary or are actually are correlating. In conclusion, we have proposed 6 new FLA metrics, and we have shown them to be statistically different to the other metrics considered. Our new metrics are also coherent and interpretable, as we have shown with the 4 test function problems. And the new metrics can be used for static FLA, and except for the 2 metrics based on the Sobol method, they can also be used for dynamic FLA. As an outlook, as has already been pointed out by some of the reviewers, we still need to correlate these new metrics with algorithm performance and problem difficulty. So using these metrics really to see if that correlates with actual solver behavior. Furthermore, we want to use these new metrics and apply them to algorithm selection and tuning methods, especially applying them to real-world problems as well. Here, constraints would play a much more important role, and we would encounter mixed combinatorial problems and also much higher dimensions in problems. Thank you very much for your attention, and I'm looking forward for the questions.